Can you see my screen?
Yeah, I can see the inside PowerPoint.
Yeah. Okay. Yeah.
Perfect.
Yeah. Hi everyone. I'm Varun Mandalapu. I'm a final year PhD student at University of Maryland, Baltimore County, especially focusing on AI in education and healthcare. So my research is kind of an intersection between these two different domains, which have some common properties. So in this workshop, my major goal in this research is to understand like how well different algorithms perform on this huge data set provided by EdNet. So the title is, do we need to go deep? And we try to understand this question by experimenting on knowledge tracing with big data. So let's see what we know. So what is knowledge tracing? So knowledge tracing is the task of modeling student knowledge over time. So how students are learning over time and how accurately we can predict their future interactions. So this is the basis of knowledge tracing. And the advantage of this, why we need to do this, is like it helps us develop systems that are adaptive to learners. So not everyone learns at the same pace, or not everyone learns every skill at the same level. So these knowledge tracing actually helps to build a system like a computer system or a virtual system that suggests different content based on task difficulty or how the learner is performing or interacting with the system. There are multiple methods. So there are three main methods. One is Bayesian knowledge tracing and some traditional methods. Here, when I say traditional methods, it is actually referring to logistic regression methods, which are adapted based on different concepts of feature engineering in learning sciences. And the final one is deep learning models, where we see DKT, SAKT, etc. So what we know so far is that deep models perform slightly better than traditional and Bayesian-based methods. So this is not my insight. This is coming from earlier research that shows a slight better chance of prediction for deep learning models. There are also studies that contradicted this claim. As we know in research, everything has its own contradictions. So there are some contradictions that show that BKT, if we tune in properly or make proper enhancements, can sometimes perform on par with the DKT, which is deep knowledge tracing. And earlier results didn't show much difference between deep learning models and logistic regression related models. Also, one of the major finding, actually this is very important work that happened in EDM, which I referred a lot. So when is deep learning the best approach for knowledge tracing? Actually published in JEDM journal last year by Gervet et al. So what they did is they compared 10 data sets on different algorithms and different concepts of knowledge tracing, and showed which one of them performed better on different sets of data sets. So we had some support from that paper as well. So what we don't know is whether or not the data set utilized in earlier research are large enough to capitalize on predictive power of deep learning models. So is the data sufficient for the DL models? This is basically the thing we are trying to find. So, and to what extent deep models perform better than traditional and interpretable models? If they do, how good they are? And can we understand, so we talk a lot about accuracy, AUC, etc., but can we understand the insights coming from these models? Can we explain what is important and where we need to focus? This helps us developing systems that are scalable as well as more helpful for the users. So the major experiment what we did is adopt the largest student interaction data set, EdNet. We especially focused on EdNet KT1, which has like sequence of question answer logs. So that is what we used in this study. And we applied traditional and deep learning models. And finally, we also used LIME. So LIME is an explanation method for local explanations, but this LIME is something that can be applied to a tabular data set, not just your deep learning models, but you can apply this particular correlation-based LIME to a regular tabular kind of data set instead of images or any other thing as well. So our hypothesis is like, we want to see if the deep learning models are outperforming traditional models with huge amount of data. So as I said, we used EdNet KT1, which has like 780K plus students, and also has close to 224 million interactions. This is after expanding cases, which means like some of the items or questions are tagged with multiple tags, tagged with multiple expert tags. So we kind of expand on that, and there are 188 cases, removing the -1 from the count of cases, and we have like 12,000 plus unique questions. And you can see the data set is slightly imbalanced with number of correct answers 152 152 million, and number of wrong answers 71 million. So this is very important as well to maintain that ratio when we are kind of interpreting something out of the models. So we cleaned the data set, and we had it's not much difference, but we had 93 million interactions, which is really good. And also the data set is following a power law distribution. So the thing is like it is concentrated at the start, but it's slowly decreasing. The reason why we look at this kind of distribution is that earlier data sets related to estimate assessments and other ITS based data sets, they followed similar pattern. Because at the end we want to see how well we can generalize to other data sets as well, the insights coming from our work. So that is one reason we looked at the data distributions, and it's similar with other data sets as well. So we did feature extraction, because first we tried to understand the impact of traditional models. So for logistic regression, we collected 4 different sets of features. So first one is based on item response theory. This is a simple one where we just one-hot encode the questions or the items present in the data set. And the next one is performance factor analysis, where we study where skills are one-hot encoded instead of items. And we also count the rescaled value of past attempts, which means like we look at, for that skill, what is the count of past attempts made by a user. And also past wins, which is like how many of them are correct in the past for this particular skill. And there is another feature set based on -3H. What -3H does is it will take time windowing into consideration. So it will select windows of data from the data set and try to count the past wins per skill, plus some of that we see in IRT. So like one-hot encoding items and skills one-hot encoding, etc. And earlier research, as I said, the one published in JIDM, they found a best combination of features that are helpful for making logistic regression more accurate. So that is adding past attempts of item and past attempts for all items to existing -3H features. This kind of improved the performance of the model. But one thing they didn't try is they didn't use time windowing concept in that. So what we actually did is the fifth set is with time windowing based features. So first we create a baseline model. Our baseline model is simple. What we do is we calculate correctness probability for each item, which is like for each question, what is the correctness probability in the training data. And just we apply that to the 20% test data set for each question, and we make that probability as the label, and we calculate the performance scores. And then we apply logistic regression on all these different feature sets, and we also apply deep knowledge tracing and self-attentive knowledge tracing models. Finally, once we get the results, we took the best algorithm and tried to explain or get insights from the predictions of that algorithm. For that, we used a Lime method based on correlations. What this will do is this will pick every sample, simulate new data points around that sample, and then make the original model will make predictions on that. And finally, once we get the outcome, we get the predictions, we have the features for each sample. We kind of calculate the correlation, because correlation will help us explain the relation between our outcome as well as our input variables. And finally, see if we can find any useful insights from that based on these correlation weights what we are collecting. So we face some important challenges. One, the data set is very huge, especially if you want to extract features. For example, item one hot encoding is around like 14,000 or 12,000 features. So that is one of the hardest thing. So we kind of reduced the data set to 50,000 students for logistic regression but we continued for deep learning. We used the full data set. So these are the results what we observed. So if you look at the baseline model, just knowing what question you are solving, our AUC is around 0.73, which is without any model for this 50,000 students, where we divide the data into 80-20 splits based on the student. And the best logistic regression features, which is a combination of -3H with -3H IRT with additional features with time windowing. So that we observed that we have an AUC of 0.77. DKT, SAKT performed well, but with 0.76 on the 50,000 student data. But for the whole data set, DKT actually the performance had a bit lag. This might have to do with how we kind of divide the sets, but it's on par. But SAKT did well, again 0.76. But one thing you can observe here is that actually deep learning models, like, they are doing good, but they are performing on par with regular models with handcrafted features or with expert engineered features kind of thing. So this is one of the insight we can get. Even on the largest data set, we can observe similar findings, which we can relate to previous studies as well. So once we observed that, we took the logistic regression model with best LR features and applied Lime on that. So this table is very important in my sense. Like we can divide the features into multiple sets. One is knowledge components, attempts, wins, and items. So which one of them help the model to make good prediction? So what this will do, this will help us understand what features are really important for the model at individual student level or at global level. So the supporting column specifies whether how well that supported the prediction, and contradicting column will specify how well it contradicted the prediction. So here it is divided into correct and incorrect predictions, which means like correct predictions are correct. So the algorithm predicted what is the ground truth, and incorrect is what is not the ground truth. So we can see that item one hot encoding actually helped very well as the knowledge components features. So these two features are kind of really good for correctness prediction, and number of atoms is a bit lagging for correctness prediction. So we need to go much deeper. That's what we thought. We tried to identify the top 3 difficult skills and top 3 easy skills. So these are based on the correctness ratio, like how many students actually made correct answers for each skill. So we tried to see how Lime is showing. So if you look closely for 142, which is one of the toughest skill, we don't know what exactly that skill is. We just have coded numbers. So for 142, the Lime importance is showing like -0.03. It means like it is really hard for the algorithm to predict that really for a sample or for a student who is answering this particular skill. That's what we infer from this. So that what is the advantage of this? We can try to adapt our model based on that, or we can try to suggest something when students are answering this particular skill kind of thing. So finally, to conclude, so results show that traditional algorithms are performing on par even with one of the huge data sets that is made available to us. And we can also hypothesize that this outcome can be generalized to other data sets which are following similar distributions as well. So that these two are important things we found. And in future work, what we are trying to look at is how much data is needed to apply simple modeling. Just take the item into account, like what we showed, like the what question you are answering, and based on that, how much probability, how much accurately I can represent whether you're answering it correctly or whether you're answering it wrongly, kind of thing. So that is what we want to look, because IRT is if you build a model based on just a question, for example, you are adding a new question to your database. it will make it harder for the algorithm to detect unless it has certain amount of data it already saw about that particular question answered by previous students or something like that. And based on importance of IRT, it is important to study its scalability. So that is one of the important questions we are trying to understand in our future work. And finally, I would like to thank you for the time. Yeah.